Hello, in this lesson we're going to be talking about the first derivative and all the different things that it can tell us. So the first thing we're going to do is I posted a PDF. You can see it right above the video, hopefully. It's good to follow along with that. We're not going to do every single thing in it, but at least it'll be a decent guide for you to see where we're going. So first is to rigorously define increasing and decreasing with two outputs, x sub 1 and x sub 2. I'm sorry, inputs, x sub 1 and x sub 2. If you think about a function that's increasing, it needs to go up from here to here, right? From the first input to the second input. So what we're going to do is we're going to say it's increasing if x sub 1 is less than x sub 2 implies the y value, f of x sub 1, is less than f of x sub 2. So you know that you've gone up. In other words, if this is your y value for the first input, then your y value for the second input should be somewhere up here. This would be f of x sub 1. This would be f of x sub 2. I think it's a relatively simple definition. You can probably write your own for decreasing, but it basically says decreasing would be the same thing. If x sub 1 is less than x sub 2, then f of x sub 1 has got to be greater than f of x sub 2. In other words, your first input has to have a larger output than your second output. So that's just obviously intuitively, I'm sure you think, well, is it going up, increasing, or going down, decreasing? So let's get into what the derivative has to say about that. The first thing is just envision a function, something like that, and you can tell clearly that it's increasing, increasing from 0 to a, right? From 0 up to a, it goes up, 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 it stops going up, and then goes down, 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 stops going down right there at b, and then goes up from b to c. So we could say that this function is increasing from 0 to a, open intervals, right? Meaning don't include a because a is the exact peak. Union B to C, again, open intervals. And then it would be decreasing from A to B, union C to, let's just say, infinity. I just threw an arrow on there that caused it to be decreasing to infinity. So this is very simple, right? I mean, looking at the graph, you can see it's going up, now it's going down, now it's going back up. But I want to be able to do this abstractly. So let's think about what the derivative is doing at that point. And I'm going to use my ruler as the derivative. Actually, I'm going to get a smaller ruler. Okay, slightly smaller. So you can estimate the derivative for yourself there. If you give it a value, you would certainly say positive something, right? It's heading uphill, the slope of the tangent line. Still, I mean, notice I'm tangent to, wherever my finger is, I'm tangent to. Still, my tangent line is uphill, still uphill, until now I've officially hit 0. So what that tells me is a function's increasing when its derivative is heading up, right, or is positive. So if f prime of x is greater than 0, then that means we're increasing. If f prime of x, I hope that prime was big enough for you to see, is less than 0, well, let's test a couple values, like there. All of this is decreasing, and in all cases, my ruler was pointing downhill So that's going to indicate decreasing. And then if f prime is equal to 0, then we're going to, at this point, say it's neither increasing nor decreasing. Think about it as sort of a pivot point, right? And you can see that those pivot points would happen at A, at B, and at C, which is obviously why I chose to label them. So it's, in this case, it's neither increasing. Oh, sorry, I made a little mistake there. This should say f prime of x is any x spot where the derivative is 0. We're not going to classify it. We're going to say it's neither increasing nor decreasing. Okay, so now let's take an example of a function. I mentioned before that I wanted to do this abstractly. So we're going to take the function x minus 5 squared minus 3. Okay, this is our function. Hopefully you have some functional awareness where you look at that and say, okay, parabola, vertex 5, negative 3. Hopefully you've had that thought already. If not, obviously get more and more, you'll get more and more familiar with these functions as we deal with them in calculus. So what we're going to do first is take its derivative, and we are very good at that. So you could do one of two things. You could expand this binomial to be a trinomial and then take its derivative, or you can do what I'm going to do, which is simply to apply the chain rule. The chain rule says 2x minus 5 to the first times 1, because there's a 1 in front of the x, and that 3's derivative is 0. So really the derivative is kind of 2x minus 10. Either of these forms, honestly, this form is probably more useful to begin with, but it doesn't matter that much. What we're going to do now is look for when the function is positive and when the function is negative. I should say, when the derivative is positive or when the derivative is negative. We learned about the intermediate value theorem before, which said that if it goes from a point here to a point here, it must have hit all the values in between. So what we're actually going to do is, if we want to find where something is positive or negative, it makes sense to do the exact opposite, to find when it's neutral, in other words, 0. So we're going to take our derivative, set it equal to 0, and then we're going to know on either side of that it has to be either positive or negative. So we will see. So what we're going to do is 2x minus 10 equals 0, and you find x equals 5. Now, I'm making a little number line here. Well, I don't have to get there just yet. First of all, are we okay? Make sure you're okay with the fact that x equals 5 is neither increasing nor decreasing. And if you think about our function, we already said that that's a parabola with vertex 5, negative 3, and it's upward facing because the quadratic part of this is positive. So we should find that it's decreasing left of 5 and increasing afterwards. So what we're going to do is we're going to take any value before 5 and we're going to plug something into it, and into the derivative. So let's take, for example, 4. If you substitute 4 into this derivative, 2 times 4 is 8 minus 10, that's negative. So I'm just going to indicate that right here to say that's negative, which tells me this thing is decreasing because it means the derivative is negative, which means that the ruler is heading downhill, which means our function's heading down. And then take a number after 5, I will take a million. 2 million minus 10, positive. So it's increasing. You think probably my choice of a million is a little strange, but the reason I like that choice is I don't have to worry about the arithmetic necessarily. I just have to deal in very round numbers. For example, on the decreasing side, I picked 4. There I really had to look at this and see whether or not it was positive or negative. Had I picked like negative, 2 billion pi, I know that 2 times negative 2 billion pi is really negative. Minus 10 is even more negative. So of course it's going to be decreasing here. So you can pick any value way back there. And you might think, well, what happens if it like stops doing whatever it's doing way back here? Well, if it were to stop decreasing, it must have hit its bottom. In which case, when I set the derivative equal to 0 here, I would have found more than one place that I needed to worry about. And all I found was 5. And the intermediate value theorem kind of keeps us secure with this assumption. So anyway, I guess for this function, point being, the function is increasing from 5 to infinity and is decreasing from negative infinity to 5. And that makes sense based on our picture. Okay, you can do this for other functions. Of course, other functions are not going to be so simple as to just go down and then back up. There is a polynomial function in the PDF that I posted, which we are going to skip. It's the x cubed minus 3 halves x squared function. By the way, when we find... So, let me maybe give you time to work through that function. Maybe you click pause and work through that next one. And hopefully now you've done that. By the way, I do think it's a very good idea not to just sit there and watch this on a computer. Really interact with it a little bit. You know, if I say pause, maybe it's a good idea that you actually do that to spend the time going through it. And then it would deepen what you're about to hear about, which is the first derivative test. Now, in this particular problem, had I only told you, if I stand in front of this, had I only given you this piece of information here, just that it's decreasing, then it's increasing, think about what that visual tells you about the graph. It's decreasing, then it's increasing. I just scooped out a minimum value. Now, is that thing absolute minimum? Maybe, maybe not, but it's definitely a relative extreme. So in this problem, what we learned from previous lessons was, okay, you take the derivative, you set it equal to 0, you find all those spots, then you have to test, endpoints and all of that kind of thing. Right now, all we're worried about is it going to be a min or a max? And you can tell decreases to increases, which means down to up. That's got to be a minimum. And of course, our picture confirms this fact. So the first derivative test basically says if f prime, the derivative, goes from negative to positive, you have a relative minimum. If f prime goes from positive to negative, you have a relative maximum. And then if it goes from, if it's positive, then positive, or negative, then negative, that's going to be neither a minimum nor a maximum. Just so you have an idea of what that might look like, think about the function y equals x cubed. Without imposing the coordinate plane on it, just to keep your thoughts a little more clear. Right here, it's increasing, increasing, increasing. Its derivative is 0 at this precise spot, right? I mean, my picture's not perfect, but it's decent. And then afterwards, oh, it's increasing again. So we would have found on a number line, this is when, now if I impose my coordinate plane on you, we would have found 0 to be like a critical point that we need to worry about. And then we would have tested anything into the derivative and found it's increasing on both sides, which means 0 is neither a minimum nor a maximum. Okay, we'll look at the half x sine x question just as an example with a trig function. Half x minus sine x. And we're only going to deal with this on the interval from 0 to 2 pi, excluding 0 and excluding 2 pi. So the first thing is to take the derivative. You probably look at that and say, like, I have no idea what this thing looks like. Well, that's okay, because when we take the derivative, we find that it's half minus cosine x. Now we're going to take that and set it equal to 0. If we do, we get 1/2 equals cosine x. Now you have to pull back to your trig knowledge and think, when is cosine equal to 1/2 on the interval from 0 to pi? Hopefully you're picturing a unit circle in your head right now, maybe a cosine wave that you can see where it's hitting 1/2, and I get 60 degrees, also known as pi over 3. I'm here. And then we're going to go around the circle. There's, sorry, I'm going the wrong way from your perspective. 0. Now I'm definitely going the wrong way. 0, 60. Now cosine's negative 90. There's 180 is now over here. We dip back down, cosine's still negative, 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 until we get over here, which is 60 degrees away from the end. So that's 300, also known as 5 pi over 3. So now we build a number line with pi over 3 and 5 pi over 3, keeping in mind that I can't take any value I want way back here or way up here anymore, simply because of the fact that the domain has been restricted from 0 to pi. So we now take, so let's say this is 0, and this is 2 pi. We now take our a point between 0 and pi over 3, such as maybe pi over 6, or also known as 30 degrees. Do 1/2 minus cosine 30. Cosine 30 is large, right? Cosine 30 is root 3 over 2. 1/2 minus root 3 over 2 is negative. And those are just a bunch of negative signs. Then between pi over 3 and 5 pi over 3 is all kinds of different values. I'll just do pi over 2. 1/2 minus cosine pi over 2, that's 1/2 minus 0, that's positive. And then if I go after 5 pi over 3, for example, maybe 11 pi over 6, also known as 330 degrees, cosine will be root 3 divided by 2 again, that's going to be negative. So you can see our function decreases from 0 to pi over 3, union 5 pi over 3 to 2 pi, and it's increasing from pi over 3 to 5 pi over 3. So there's that process, and that's what the first derivative can tell you about a function. I will leave the rest of any of the stuff on the PDF for you to do. And the easiest way to confirm all this is all you have to do is do this whole process abstractly, type it into your calculator, the function, type the function into your calculator, not the derivative. And then just observe, did your intervals turn out to be the way they turned out to be with the function itself? So that's that, and that's everything the first derivative can tell you. Again, it was, is a function increasing or decreasing? When does it pause or hit peaks? And then the first derivative test said, okay, if you know when it's increasing or decreasing, you should also be able to locate relative minima and maxima. Okay.